Well, I guess I'm here with Paul March, and I guess let's go over the Woodward effect and the STAPE conference in general, because we've been interacting with the last couple of years now, and STAPE has been one of those. I missed it last year, so I wasn't able to kind of see some of the work there, but this year the Woodward effect, as I discussed earlier with Andrew Palfreyman, this is compelling material, and you guys have put together really this three-paper overview that covers several different experiments, 2/3 of which were highly successful, and the others I actually kind of wondered about, I felt were a little bit questionable. So,
well, again, Jim Woodward and the Woodward effect, the mass fluctuation proposition that Jim Woodward has proposed, has been verified to some degree by Jim in his own personal lab. I've done two verification tests that showed a marked effect. No noise issues no noted noise issues that Jim has been fighting with because of the frequency of operation that I run at. And the ARC test from Vienna showed that Jim has noise issues, and they were having noise issues. But if you look at their data closely, there's probably an effect there. Jim's convinced, he sees it. The Nimbo and Martin from Tamar, from ARC are new to the game, so they want to be a bit more cautious.
Yeah. Well, some of the things that we discussed earlier are, now again, Andrew is working in the higher frequency range, I think 100 megahertz. Yours is
the 2 to 10 megahertz range. Where I'm concentrating.
So the scalability here, though, is taking up. He's looking at potentially up to 60 kilos of thrust.
That's right.
And it looks like, as you guys improve your equipment, your test procedures and scales and stuff like that, you guys will be able to continue to improve this output to just radical.
Okay. If mass fluctuations exist these are transient mass fluctuations. If they exist per Woodward's proposition, hypothesis, then these type of devices will be able to be scaled up to megatons of force. We're talking F1 Saturn class engines. This is 1.5 million pounds per of thrust.
Sure.
But that's way down the pike. We're still at trying to get up to a gram level. What I saw was 0.4 of a gram with one device, 0.5 of a gram with another device. With two different measuring systems. So I'm fairly confident what I saw was real. The next step is to go to a device that can get maybe 1 to 5 grams. You have to do this incrementally. You just can't throw a dart and hope you hit the ball.
Sure.
Because most of the times they don't stick.
Yeah. Well, and I guess it's important to also lay it out in terms of one of the things that makes this important in terms of our applications is I by no means want to say that these things are easy to build, because you guys have put hundreds, if not thousands of hours of effort as well as dollars of your own money into building these things. But at the same time, this is also the kind of thing where replications can be done using somewhat commonly available equipment.
That's correct. The components are easy. It's commercial off-the-shelf capacitors. It's inductive wiring, just coil wire you wind, and it's the RF systems to drive it. It's the knowledge, the multidisciplinary knowledge that you have to understand to some degree. You don't have to be an expert in any of this area, but you have to know enough to know about electronics, about basic physics, about systems integration issues,
sure,
about aerospace thrust-to-weight ratio issues. Those types of things you have to become familiar with, and unless you're comfortable, you can get lost real easy.
Well, but the advantage though is, given a little bit of time, given a little bit of diligence in assembling one of these devices, unlike many of the theoretical pieces that we've seen over the last few days, this is something where the experimenter can sit down, start constructing it, and there's a very good likelihood that they could see noticeable results, possibly even have the thing take off the table at some point.
In some time, yes, and about 3 generations down the pike, we might be actually get it to hop off the floor.
Well, one of the things I'd like to ask about, because Andrew didn't touch on this too much, was Tony Robertson's work in terms of he restructured
based on the E&M Jackson, the classical electrodynamics work from Jackson. He's the god in electrodynamics. I'm not familiar with the paper. I knew of it, and I saw the first rendition of it, though Tony changed the last half, and I hadn't seen yet, and I really don't understand exactly how he did the last 2 charts. So I got to get a copy, and that's not in his paper. So I got to get a hold of the charts from Tony, and then see if I understand them. And key one, how is momentum transfer being implemented? He was not sure. Maybe it sounds photonic since it's an E&M electromagnetic approach, but I don't know yet.
Yeah.
But it's interesting that he found a way to make Hector Brito in Argentina's, Jim Woodward in California, mine in Texas dovetail where it all makes sense.
Well, also, it sounds like he's reformulated Jim's theory into kind of another theoretical format that predicts the same results. I think that's important theoretical validation for it.
It is. It could be. It could be. It depends on how many assumptions he made along the way.
Sure.
And I don't know what his underlying assumptions were and whether those are valid assumptions.
Well, I think the other thing that also impressed me about that was the restructuring that he had done mathematically. I think his output was something like 100 newtons, so he was predicting something around 25 pounds. And again, he listed out several specifics that could be experimentally derived.
Sure.
And he had changed a few parameters. Instead of the piezo-based approach, he actually went to, if I remember right, a magnetically based approach.
Electrostrictive.
Electrostrictive. Okay.
I think that's what he said.
Magnetostrictive.
Yeah. I'm sorry, magnetostrictive. Right.
Yeah.
Which, if you use, there's other materials that might be more applicable to that approach, but we're using barium titanates, and we know those materials, and I think with those materials we can get at least pounds of force out of them.
Sure.
Multiple newtons.
Well, the impression that I got, one of the things that just continued to just amaze me was, a lot of times a theory comes along, or perhaps an experiment, maybe the lifter might be like something like this, and we look at this experiment, and there's a little bit of potential there, but you look at it and say, how do I scale this? Where can it go from here? And what you guys have done, in a way, it almost reminds me of Columbus landing on the New World. He didn't just land on a beach. This beach is connected to a whole continent with full of new ideas and riches to explore.
Exactly. There is so much. If the mass transients are correct and they exist, that's okay by Mother Nature, then you open up the entire electrogravitics wonderland. Anything you ever thought about electrogravitics is available. You'll have to have a little bit different mindset than what's currently out there in the UFO community, but it's doable.
Well, yeah, and actually even to address the UFO community's kind of perceptions, I guess, the Star Trek type stuff to some degree. But even looking at it from that perspective, it is interesting that the monster in the closet, I guess, is the wormhole territory, which may open up some really strange effects.
The wormhole effect will allow us faster than light communications, instantaneous effective. It's related to quantum mechanics, entanglement issues. I'm sure they are, like this as far as the explanation will tell you how the other happens. In addition, you'll have instantaneous teleportation from point A to point B. And as long as you can move the exit port of the wormhole generator to the moon, the Mars, go out to wherever you want, you end up with a teleportation system that's near instantaneous. It's not totally instantaneous. It takes several nanoseconds to make the transfer.
Yeah, I wouldn't complain about that. well, also the negative, I mean, having Eric Davis presented on traversable wormholes, and one of the common challenges with wormholes.
And Eric, by the way, is one of the leading experts in that area.
Yeah, Eric is amazing, and he's so dynamic. He's a dynamic speaker. But his presentation on traversable wormholes opened up this idea, I guess, about these things are really achievable for construction. The problem is the negative energy to keep them open. And the part that struck me about that, again, I could be off base on this, but the thought was, typically when we look at generating negative energy, we're looking at doing it from like an electromagnetic perspective. And so you're going energy to energy, right? You don't have any savings there. But you guys are on the other side of Einstein's equivalency principle, where the negative mass that you generate is theoretically equivalent to negative energy in many ways, but it's equivalent to, I don't know, kilojoules maybe? Tons and tons of negative energy. I mean, lots of it.
The energy issues are still unresolved. That's one argument that Woodward and I and Andrew get into. We go in this round robin, and we're still not sure exactly how the ultimate energy, whether this can be used for energy production. I think it probably can in the analysis, but that's TBD at this stage.
Yeah.
But it certainly holds promise.
Well, I think you guys have done something unique in that it's one of the few experiments, much like the lifter was a few years ago. It's one of the few experiments that captivates people both on the experimental level, people surfing the web looking for anti-gravity ideas, as well as people at the Air Force and DoD level who are also here at the conference looking at
Exactly. And one of the things, by the way, that the Air Force guys were telling me what they want to see before they will even acknowledge it is that they want to see a MLT, a Mach-Lorentz thruster unit, either on a ballistics pendulum in a vacuum chamber or in a Hero's steam engine type of spinner, with the reverse thrust like this, and it spins around a pivot point, in a vacuum where it moves on its own power, and then can back up when you reverse the phase. Given that demo, having the thrust and being in a vacuum where there's no ion effects or very little, and being able to switch the phase, as the theory says we should be able to, and then rotate back in the other direction, back up. If we can perform that, we're off to the races, guys.
Yeah. Well, I'd like to ask a little bit about what's coming up over the next year. By the next, I'm hoping you guys present at State 2007, about a year away. And
if somebody sends me the money.
Yeah. Well, I mean, in terms of output effect, what would you anticipate in terms of...
I'm hoping for something on the order of 1 to 10 grams.
That's good. That's good. I mean, that's...
My next test article that I'm going to be, I've collected the parts. I've got to fabricate the pre-PC boards and all the windings and whatnot. It's going to take about 6 months to build on a part-time basis, which I do all this, in the home lab, on my own nickel, etc. It'll probably take about 6 months to build. It's going to be a device maybe about a 4.5 inch, 5 inch diameter circle, and it should, if the spreadsheet that Andrew and I developed is anywhere close, we should be at least in the 1 to 10 gram range, with a mass of on the order of maybe 300 grams in that ballpark. So you're talking about a thrust to weight ratio of maybe about 10% or thereabouts.
Yeah, well, and I guess
and that's big enough to do a thrust pendulum, or rather a ballistics pendulum, or a pinwheel if you built two of them.
Yeah, well, and for people who might not be, some people might look at it and say, well, that amount of grams isn't necessarily as much as I hoped for. But I think the thing that the audience should recognize also is you guys are going up an exponential curve here, right?
That's correct.
So it's 10 grams next year, 100 grams after that,
and 1,000 grams, and we were up to a kilonewton, or rather a kilogram, which is 10 newtons.
Yeah.
And it's going to be an order of magnitude every year with the current baseline, I think, as far as what are projected. We could run into a roadblock in materials technology, just like getting capacitors that have no metal electrodes versus the silver that's the standard commercial off the shelf.
Oh, sure.
Because otherwise they don't last very long. The commercial off the shelf caps last only on the order of minutes to an hour or so max operational time. That's a laboratory curiosity. That's not something you can rely on.
Well, I guess the other aspect I'd like to touch on is, because you're describing the technical details of this, one of the thoughts that had occurred to me, because, well, it's kind of a selfish thought, I'd like to build one someday, is in terms of putting together a replication guide. Again, it's a horrible comparison to compare these to lifters, because in so many ways they have so much more potential. But one of the things that really sparked the lifter revolution, if some people have called it that, I guess, is the easy availability of step-by-step plans. And I've wondered if you guys have thought about collaborating or possibly working with us.
Yes, but the objective is to have a unit that was reliable, lasted at least 10 hours, would produce sufficient thrust-to-weight ratio to be demonstratable with a ballistics pendulum. A ballistics pendulum is where you have two strings off the device and it swings up from the ceiling, and it comes up and holds, and then you reverse. It doesn't oscillate. This comes up and holds. That's telling you you've got a constant force holding it.
Sure.
And then you reverse the phase between the B field and the E field, whomp, and it'll sit there and go the other direction. And that demonstration, especially in a vacuum chamber where you don't have any contamination from ion, wind, other issues like that, is the demonstration I think everybody's looking for.
Yeah, absolutely. Well, now I guess the other thing is the money aspect of this, because you guys all put thousands of dollars into building these things, and in some ways having the feedback from kind of I don't know what you call the authority figures, right? Like the Air Force and others. They mean well, I guess, in terms of they have a hard time selling these projects internally, especially because it's kind of far out to some people. But I'm also bothered by the fact that, you know, every year continuously it seems like, you know, they're going to be coming back saying, well, if you do this for us, then maybe we'll fund it. Well, you're out another 10,000.
The carrot and the donkey.
Exactly. And you reach a point where it's like, well, we apparently didn't need your funding in the first place because we paid for it ourselves.
And that's what they would like. The managers, the money managers want a safe bet. They don't want to, you know, expose their butts to their bosses who say, why did you spend this $100,000 on a crackpot idea? You're out of here.
Well, I guess the caveat, though, would be by spending $100,000 on it now, they would at least have some feeling of ownership, whereas if they wait until you guys build it out yourselves, then they'll have to buy them for $5 million each like everybody else.
It's always short term.
Yeah.
This country is built on short-term thinking. You look at the stock market, the monthly reports, the quarterly, you know, profit margin reports for the companies. It's all built in that 3-month cycle.
Sure.
And until we have a little bit farther thinking, 5 to 10 year scope, that's the attitude you're going to get.
Yeah.
And that's what we have to live with.
Well, now you mentioned the capacitors, and extending the capacitor life is a big part of that. And then I guess Tony had touched on the concept of the magneto-restrictive materials. Mm-hmm. But you know, are there any other? Because one of the things I know that you've thought about in the past is including nanomaterials and some of the new breakthrough materials out there. There are actually a lot of potential technological avenues just based on better materials to make these things perform better.
There's a whole venue that uses gaseous materials, high-density mercury plasmas, for instance, in tokamak-like reactor structures that could express the same effects. These are high-dollar things, only done after we're convinced that there is a payoff.
Yeah.
First off, you do the cheap way, and you do the small-scale way. And then you say, okay, what's a usable thruster design? Something that could produce several thousand newtons, and you know, have an array of 3, 6, 9, 12. 12 you can slap on your car. Back what Doc did with his little DeLorean and Back to the Future. I mean, you got your flying car finally.
Well, yeah, actually that's an excellent point, because one of the nice things about the small size and also the modularity of these devices, because, you know, a lot of the designs, like, you know, the Searle effect generator, right? It's this big...
It's all or nothing.
Yeah, and with this device, you can use a small generator, or not generator, but a small thruster, propulsor, here or there, and you can place them in different positions.
That's correct.
And so you might end up with something that is very much like a car, but you wouldn't really have an engine.
Think of the Borg cube. It's a redundant, multi-area, multi-modular approach of thruster design. And you can put them anywhere.
Sure.
In the vehicle. Whatever convenient to physics, i.e. moment arms and torquing requirements, you have to salute that issue. But also, I want it in the wheel well instead of, you know, over here in the back end, because I have to, you know, throw stuff off the back end.
Yeah. Well, I'd love to get some photos later of the device that you have, which was actually built inside of a little tin can.
A little Minwax tin can. I went to the Home Depot, got a can of Home Depot stain, and that's what that can is.
After using it on the deck, right?
That's right.
I do the same thing. And so, you know, you have this tiny little, I mean, this can is maybe 3 inches tall, maybe 3 inches diameter.
3.5 inches in diameter. It's 3.5 tall, 3 inches in diameter, weighs, the total assembly is 144 grams.
Yeah, and so you would have to expect, I guess, now your commercially available thruster, part of it would depend on how much you need for output, but for a lot of tasks, I guess, you might have something not much bigger than that, and maybe a couple of feet at the outset for a vehicle.
Typically, I think thrusters that would be usable for a vehicle are going to be on the order of maybe 24 inches long, 3 to 6 inches in diameter, and you're done.
That's maybe about size. That's almost about the size of a 2 liter of soda bottle.
A 2 liter bottle would be great. Yeah, that's a great.
Yeah.
On that order.
So yeah, instead of tossing 2 liters in your trunk to take them home to the kids, you've got 2 liters mounted inside the chassis, figuratively speaking, the same size, that are lifting up your vehicle, flying it, providing directional control and stability and redundancy. So
you need a triplet of those in each wheel well. So like I say, for full 6-axis control. But again, that's 3, 6, 9, 12. That's 12 thruster modules that you bolt on to the wheel wells, because that's where it's optimal to put them.
Sure. Well, I guess the To follow up on that now, in terms of providing power for these, what are the power requirements for these devices?
Not that high, depending on what the ultimate operating frequency was going to be. Probably on the order of kilowatts per module, no more.
You know, it almost sounds, as I understand it, increasing frequency increases the thrust. And it reminds me in a way, it's almost seemed like a cheat to me in electromagnetism, that the higher the energy of a wave, the shorter the frequency. It's not the wave isn't larger, it's not more powerful, it just has a higher frequency. And it seems like the higher frequency adds something.
It's just a matter of how many energy pulses you get per second. That's all there is to it.
Yeah.
At 60 hertz, you're only getting it 60 times a second. You integrate each pulse. You know, that's 1/60th of a second. That's all that's available. You start doing that, back up. You add a high fallback input on that. That frequency dependence is very much a matter of what you're dealing with, what you're trying to affect. Because in the Woodward effect, we know that the mass transients increase proportionally to the cube of the frequency, because that increases the acceleration loads that the ions see as the faster transition between positive and negative swings in the voltage increase at those rates. That's pretty much, that's experimentally verified.
Sure.
So there's another issue, and I'm trying to think of it, and I've forgotten it, on the base business about frequency. Actually, as frequency goes up, if the amplitude holds the same, the actual energy contained hasn't really changed. But that's just if you're talking about electromagnetic, equivalency.
Yeah. Well, and the efficiency increases the frequency. So
possibly, it depends on the device.
Sure. Well, and so in terms of power sources, I guess, for this thing, we're at a conference that features these radioactive thermoelectric generators.
First off, it depends on how long you got to source it. If you're talking minutes, batteries. If you're talking hours to days, fuel cells. If you're talking months to years, nuclear reactor. It's a matter of how long you got to source the supply.
Sure. Well, do you think you'll have a design stable enough to run for like a year continuously? Is that foreseeable, or is that something that...
It depends on the materials.
Well, and again, it doesn't fall, having to replace components falls well within the automotive model. We've seen that for years.
Of course, you have to reach some type of, minimum operating time of, 1,000 hours, 500 to 1,000 hours minimum per component before you got to replace it. That's acceptable.
Yeah.
Once we get to that level, from minutes to an hour to hundreds of hours, then you have a commercially viable product.
Yeah, absolutely.
And that's going to take a lot of material technology development, and that's where the bucks are. That takes a lot of time and a lot of skull sweat.
Well, for people to start learning about this, I published a few things on American Anti-Gravity, but I guess the website that Peter Vandeveer has built for Jim Woodward is woodwardeffect.org, right? And do you have a website yet, Paul? Or? But you have it published occasionally on ours, and again, we're thinking about doing some plans, or at least something to kind of help the public get a better feel for what goes into building one of these. And I'd love to be able to publish you guys' presentations, because these were just so rich with information, great photos, great layout, and there was real flow to these PowerPoints.
I'd be glad to give you my PowerPoint. That's my property. That's not AIP's.
Unfortunately, there are some challenges in covering state.
Yeah, I know.
Well, actually, to follow up on that briefly, what are your thoughts on this year's conference in general?
It was kind of depressing the way because this is primarily a nuclear power and propulsion area. The advanced propulsion stuff that we do is a sideshow, to be quite honest with you. It's only been going for 4 years versus 26 years or so for the nuclear. And since Mike Griffin at NASA, scuttled the nuclear program for NASA for the next 10 to 20 years, there was a lot of long faces around here.
Sure.
I think there's a palace revolution in the making, from what I'm hearing from several people who are powerful, who are going to try to change the mind of Dr. Griffin. Whether they are successful is still up for grabs.
Yeah.
But I think it's a bad decision. Even if they are really tight on coin, which the space program is right now because of Katrina, Rita, the war on terror and all the rest of the requirements and the humongous deficit, there's still room to put a moderate, 10, 20, $30 million out of a $16 billion budget for areas in the nuclear program and advanced propulsion research. And not just say, nobody does anything because you're going to break up the teams. It's going to take 10 years to reconstitute minimum.
Well, given NASA's, I guess you'd call it operational challenges, the requirement, as a few of the NASA staff, because there are a number of NASA people here at this conference, as a few of them have mentioned to us on many occasions, NASA has deadlines and goals that are congressionally mandated that they have to meet. They don't have any choice in that.
I know. Griffin is between a rock and a hard place.
Definitely. Well,
I'm not really bitching at him. I know the decisions were tough for him.
Yeah. Well, my question though was, in terms of advanced propulsion, given these challenges and these requirements for NASA, I mean, is it possible that maybe a new agency might be better able to handle the advanced propulsion stuff than NASA alone would?
Yes, definitely.
Yeah.
But you have to get the White House to agree. And that's the biggest. You need legs and be able to have sufficient data to back up your position that you can tell the scientists that are of the old school who don't really want to address this issue, aren't familiar with it, and demonstrate the pinwheel, the ballistic pendulum, and say, guys, there's a whole new paradigm here. We better address it.
Absolutely. I totally agree. Well, Paul, thanks again for your time. Again, we've been speaking with Paul March on the Woodward Effect, the MLT thruster, and the STAPE 2006 conference.
Thank you much.